All right, welcome back again. It's good to be back, but I'm only back for 2 class periods in person. Both classes next week are going to be virtual. There'll be a set of recordings that you'll have at the end of the week. I feel like that'll keep us on track a little bit more. Next, today we're going to be covering the example R file that I started on 2 weeks ago. We'll sort of start over again because I didn't really do a good job, I felt like, with it. We'll cover it hopefully in its entirety today. The homework will have an extended deadline. I haven't decided if it's next week or the week following. I'm actually going to just say it right now. I'll give you 2 more weeks on it because a lot of the things that are involved in the homework are involved in the class today. And for those of you who've taken a Lisa Hoffman class before, it's literally a Lisa Hoffman homework. So that will help you, but we're going to do it in Bayes, and you can go and ask Lisa Hoffman how she feels about Bayes. Okay? All right. And her answer is incorrect. You just tell her that right now. Okay? Okay. Anybody volunteer to do that for me? All right. So, any questions before I start? Anything you'd like to know about? That silence indicates there are none, so I'm going to move on. Today's class, if you're on the server, it's in class files, lectures, lecture 03 example. That is where we're at today. And then that example file is what we'll be using. I'm just going to set the working directory into that folder. Okay. So what we're doing today is running through a Bayesian version of the linear model that we started with in lecture before. Remember, we had this, what I call fake diet data, where we had basically a set of 30 people. They were put into 3 different diet groups. We had their height in inches and their weight in pounds. Our goal is to predict weight in pounds as a function of height in inches, the diet group they're in, and potentially the interaction between the two. And as you saw in the previous recordings, we had some plots of these data. Long story short, I'm pretty sure these are fake data because take a look at how well these lines predict each observation. I think our R-squared was like 0.98. Pretty darn good. Although I will say, I recently presented a result at a conference a couple weeks ago where I had an R-squared about 0.9. So, hey, with real data, R-squared Hall of Fame worthy. But I digress. Anyway, how many of you have seen an R-squared of 0.98 before in real data? Nah, I don't think that's possible. Well, at least not in social science data, at least. Maybe when you're over in the hard science, where things behave a little bit better than people. All right, there's humans. They're just so messy. Okay. I'm going to center my variables right here. And the full model, if we were to run this in a frequentist approach to get started with, just to get us remembering what we're doing, we're going to have weight in pounds as predicted by height in inches. Now, remember, we're centering height in inches so that the 0 point is at 60 inches. Right? This will become important when we start talking about prior distributions, potentially. We are going to create a factor or dummy code variable for diet group itself. So there will be, because there's 3 different diet groups, one of those will become the reference group, and there'll be a dummy code, a 0 or 1 for the one person who's not in the reference group. And then we'll have a height by factor interaction. This, if you're thinking about what this the name of a type of model, this is like ANCOVA with an interaction model. I don't know if it has a name. At some point, we could quit naming things and just start letting the math take care of it for us. So there's our full model. If we do a plot with what we end up having, let's see. Come on now. Yeah, we got our residuals and stuff. Here's our ANOVA table. You can see that we have a significant diet by height interaction. We have a significant effect, or main effect of factor, and we have a significant height main effect. I believe in R's ANOVA table, these are marginal effects. So the difference, if you remember in linear models, when you have an interaction term, you have to understand whether an ANOVA table describes the conditional effect, meaning when the interacting variable is equal to 0 or not. But I believe the sums of squares table, ANOVA table in R, is actually marginal, meaning it's irrelevant to whether group. But here are our coefficients. Again, now these are conditional, right? So we have our intercept. This looks like a person who is at 60 inches tall, and in diet group 1, we expect them to be 147.5 pounds. We went through this the last time. you can go through the video to see each of these other values. That's less the focus of today and more the focus of your homework, and so I'll leave that to you for homework. Sound good? All right, the part you're here for is Stan, and that's what comes up next. Can you all see the font on my screen okay? Does it seem okay, large enough? Does anybody need it bigger? Okay, plus you can zoom in on your own Zoom, I think, as well, too. There's a way to make it big on your side. Okay, so in Stan, remember there's blocks of syntax. Here we have data, parameters, and model. I like to start with model to begin with, because that tells us what we need to import into Stan and what tells us which parameters we need to define. So here, weight in pounds, we're just going to say is a variable we're importing into Stan. And if you look at the linear model distinction, this linear model itself, remember in what we're saying is weight is equal to the sum of each of these predictor variables times the regression coefficient. Each of the predictor variables, though, are entered without assumption, so they're effectively fixed. They do not change any distributional assumption about the weight itself. So what that really equates to is that weight follows a normal distribution where the mean is conditional on our linear regression. And what's left over, the variance, or in this case, the standard deviation, sigma, is the residual value itself. So we say that weight in pounds is normally distributed, but we put the linear model for the mean in the mean section. And then the variance or standard deviation section, we put a parameter sigma. Now, many times when you've done a linear model before, you've never had to break that down, where you've had to describe what's the mean and what's the variance. In Lisa Hoffman's multi-level classes and some of her introductory courses, you will have heard the model for the means and the model for the variances. How many of you have heard that term before? Seem familiar, right? Turns out those are distributional assumptions. When you write out a linear regression like this, that's literally what you're assuming. And in Stan, we have to go and provide that in syntax. So we literally put the regression coefficients in the model for the means. So here, beta 0 is the intercept. We have a slope called beta height, multiplying a observed variable height 60 inches. We have beta group 2, which its regression coefficient times an observed variable group 2. Group 3 times an observed variable group 3. So what I'm getting into here is you can see this whole long line. The betas, the terms that I start with beta, are parameters. So every time we put a beta here, it has to show up in the parameters block. And I like how RStudio will highlight that syntax for me here, right? So every one of these parameters will show up. You can see the highlighting as I click through in the parameters block and syntax itself. Finally, we're left with sigma. Sigma is a parameter here. Oftentimes, it's the forgotten parameter in linear models from a least squares or frequentist maximum likelihood type approach, but it's still a parameter and we have to estimate it. Sigma shows up in the parameters block, and sigma has a lower bound of 0. Any questions about any of this so far? Okay. I would say the hardest part to me in the Bayes sense is thinking what the distributional assumption of your outcome variable happens to be. Because it's not as simple as just saying, I want to predict this variable with these predictors, right? Height and 60 inches and so forth. It's knowing the distribution that you're implying with it as well. So Bayesian statistics, to me, helps you learn a lot more about statistics in general when you have to code things like this. Okay, so I mentioned all of the parameters show up in the parameters block. Once I highlight all these observed variables, you'll see those in the data block up here as well too. And so one thing to get used to doing when you're building your Stan syntax is to ensure that your parameters are listed and your variables, your data are listed. Now, Stan will not run unless if you have the data not listed. So in many ways, Stan will keep you from sort of hurting yourself in that sense. But sometimes, to me, when you get much more complicated models, like some of our psychometric models, you'll have a lot more parameters involved. There are some shortcuts I will teach you in the next couple of weeks, a couple classes, about how to make Stan syntax a little bit shorter, a little bit more effective. But for learning purposes, this is how we're going to write out the entire model. And then what I'm going to encourage you every time, including when you do complicated models, is to start simple. Because if you start with a very complicated model and there's an error, it's hard to figure out where that is. But if you start with a simple version of a model and you start adding terms to it, you can check to see where errors happen as you add terms. So just remember this. Go back to basics. Even for the most complicated models, start very, very simple. Okay? Questions? No questions. Good. Moving forward. So now, with our stand syntax, we have to go build a stand list, an R list object to send to stand to do the processing. And the list itself should include each one of these variables. N being our sample size, and then each of the this is weight in pounds is the outcome, and then each of the predictors themselves. Right? Now this is where stand will not normally check you unless you insist it does. So here, N, we define it as, remember, we have to define each type of variable as we put into stand. It's an integer. An integer is a variable that's a whole number. You can think of it that way. They can be positive, they can be negative. We put a specific check into stand right here where lower equals 0, meaning if we submit an integer for N that's below 0, stand will not run. It'll basically say this does not fit the data I'm expecting. You can put in as many checks as you want in stand with lower or upper bounds. They're very helpful because oftentimes when models don't converge, half the time it's because the data you're sending into stand are not quite right. So just as it does help to add checks, and as I would encourage you to do so as you're new to stand, wherever you can, add checks. Okay? So let's go and build that itself. So group 2 is a dummy-coded variable which equals 0 if a person's not in group 2 and equals 1 if a person's in group 2. So that's that variable. Group 3, likewise, is a dummy-coded variable where it is 0 if a person's not in group 3 and 1 if a person's in group 3. All right, so far so good. Our interaction variables are the product then. The product of our height variable times our group 2 variable. So in this case, height times group 2 will end up with the height centered at 60 wherever there was a person in group 2, but zeros elsewhere. Because as you would see, a 1 times a value will lead to the value itself, whereas a 0 times a value is always 0. Similarly, height times group 3 will do the same thing. You'll see values where people are in group 3 and zeros everywhere else. So far, so good? Okay, so far, any questions on variables? Okay, so now we build the stand data object. It's a list. What stand is looking for in the list is the name of each variable. So here where I have N, weight in pounds, yada, 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 etc., that mirrors exactly the names of each of the variables that I'm specifying. And I say exactly. Remember, R is case sensitive. So if you put a capital letter, W, instead of a lowercase letter, it will throw an error. Stand is also case sensitive. R and stand are such sensitive beings. They're such fragile, fragile things. Sorry, making a joke. You ever thought of R as fragile? Probably more annoying than fragile, right? Anyway. The stand data object itself then is the list. You'll see each one of those names that I called in the data block in stand are now the names of each of the elements of the list. For those of you who are new to R or somewhat shaky on R, an R list is an object that is a collection of other objects. So you can have lists of lists if you really wanted to. Right? You can have lists that has one part that's a data frame, one part that's a vector, one part that's a character. So a list is just a generic container of all the data that you have in R. So that's the first part. The second part is to compile the stand program. Right? So remember what stand is doing. It is taking this syntax right here in R, saving it to a text file, and then CMD stand translates that text file to C++ and runs a compiler to build an executable object for it. So that thing is now fast and specific to this model itself. So if you wanted to run a general linear model on some other piece of data, if you look at how I specified my model in R, it wouldn't work unless you had exactly these variables and exactly these inputs, right? So this is a very customized stand file. In our next class, I will show you how to make it less custom, particularly for linear models. you can make things work a little bit more automatically. And actually, the culminating part of the Lecture 03 sequence will be a Stan file that basically does all of intermediate statistics if you wanted it to. But that's later on. You can get much more complicated in Stan. All right, shall we run this? Let's run this. Once we build the Stan object, remember this is what's called an R6 object, so it actually has functions embedded in it. So we put the $sign and the word sample afterwards. Sample is a function, right? It's like using LM, but it's built into an object. In that sample function itself, here are the options we're going to give it. We need to tell it our list of data right here. We need to tell it a random number seed. Remember, in random number seed is a number that starts, that basically, when you know that number, you know all the sequence of random numbers that comes from it. So the seed itself can be okay, it can help in reproducing a result, but I will say that Stan, because it's, depending on architecture of a computer and how it's built for parallel chains, it may not exactly be reproducible. The Stan manual talks about that as well. But in general, if you were to build your own Markov chain and had control of a little bit more of the features of it, you could build it to be the same result with the same seed. We'll have 4 chains. Each of those will be running in parallel. So what we have on this server is we have multiple cores, right? A core is a computing unit that runs by itself. These chains can run all at once, which means the 4 chains will run in a little bit more than a time it would take one by itself. If you do not specify parallel chains, it will run one chain only, and then it will run another chain, and then it will run another chain, then it will run another chain, all in sequence. So it'll be 4 times the time. So parallel chains, big important thing to do. Okay. Most of your local computers will have at least 4 processors as well these days. Most of them have 8 to 12, and then if you get really fancy, you'll have a whole lot more than that. So the warm-up, we're going to run 10,000 warm-up iterations. Remember I mentioned before, picking how many warm-up iterations is difficult. 10,000 is likely a lot for a linear model. A linear model is a model that's fairly basic, that will be able to run fairly well with short numbers of chains, but we'll do 10,000 just in case. And then sampling, so we run 10,000 iterations for each chain. We discard those iterations, and then we sample from the remaining 10,000. Okay? All right, here goes. That didn't take too long. Took 1 second. Not bad. You should be so lucky if the rest of your models work that way. All right. What's the next step we do after we've run our model? You can see it right here. Line 113. We need to see if it converged. So one way we can see it converged is to have Stan output the summary for all of the parameters. So the summary function, once you run this model, summary is a function that applies to the object that it builds, right? So our object now, if you think about it, has a Markov chain that has just run. Here's our summary. Here's the R hat column. This R hat, we want it to be 1, and look at all those R hats. They're all 1. It's pretty good, right? Now, if you have a lot more parameters than that, which you will have in a psychometric model, because in a psychometric model, not only do you have item parameters, you have person parameters. So if you have 1,000 people in a data set, if you have, let's say, take a unidimensional IRT model, 2-parameter model with 1,000 people and 30 items, there'll be 60 item parameters and 1,000 thetas. It's 1,060 parameters. I don't want you scrolling through 1,060 lines to figure out if there's a 1 above 1.1 or something like that. Let's take the maximum of it. So here, the maximum function will work, and you can see the maximum is 1.000245. So would you say that this is converged? Yeah? How many of you think it's converged? How many of you are paying attention? If you're paying attention, put an L on your forehead. I'm just kidding. See what I can do on Zoom here. All right, it's converged. Am I right? How many of you are confused? Yes, question, James. Oh, no problem. No problem. Okay. No question. But it's converged. Let's take a look. We can actually plot most of this. Whoops, wrong button. These are the time series, which should look like, as Vladimir mentioned, a fuzzy caterpillar. I've never really said this about plots before, but you want these to look cute like a caterpillar. I don't know, are caterpillars cute? I'm sorry, I'm trying. I was just in South Korea. I'd never been before, and I was told by one of the locals that Koreans like cute things. And there are a lot of cute things. A lot of like stuffed animals and stuff like that. Pretty cool. So here, but if you were to visit me, like, I'd have pictures of time series on my plot. Oh, that's a really cute plot. Look at that. But generally speaking, these look pretty good, right? They don't see any trend. You do see a case or two where you might have an extreme value. That can happen. But generally, the pictures are the same. And this is corresponding to what we talked about with the R hat. Remember, R hat is essentially a ratio of between chain variance to within chain variance. And if the between chain and within chain variance is equal, you get an R hat of 1, it looks like this. Right? So that's good. You can also then plot a histogram of the posterior density. So this is a histogram of each of the parameters. Right? So once we've taken and we've seen that those chains have converged, the next step is to discard which chain each of the sample came from and put them all into one big pile of data. Right? Then summarize that data. So there's our plots of histograms. And the density function is a smooth version of the histogram. Think of it as a histogram where the size of the bin is smaller and smaller and smaller, really, really tiny. And then to make sure that the line is roughly even, so it's not so jagged, it tries to sort of have a moving average of plots of places. So this is really a nice shape of each of the parameters. This LP is log posterior density. We don't often look or talk about it. Now I will note both of these functions take a long time when you have a lot more parameters. And so what you can end up doing in each is there's an option for which variables, right, that you can choose. And if you give it a list of parameter names, it can select it. So for instance, if I only want to look at beta 0, right here, it would go a little bit faster and you would get just beta 0. Any questions? So far, so good, right? Let's take a look then at our results and compare them with LM. So here is our estimate for each parameter. Our LM estimates, our least squares estimates right here are first, and our Stan estimates are second. Okay? So what do you notice in general about our estimates? The estimates from least squares and the estimates from Stan are fairly close in value, right? So when we talk about a Stan estimate, we're actually talking about the posterior mean in this case, right? Does anybody remember the Bayesian version of what we call posterior mean, the more complicated Latin version? It's not even that Latin, sort of a combination. We abbreviate it to 3 letters, EAP, expected a posteriori, right? Expected, that's your way, the word mean, sometimes in statistics we call it the expected value, so that's why we sometimes refer to it that way. So the EAP estimate from Bayes and the point estimate from least squares are fairly similar up to at least maybe 2 decimal places, right? Not bad, right? But there is a difference. And the bigger difference is in the standard error. Why do you think that's the case? In fact, not only a difference, it's a very big trend. Each one of our Bayesian standard errors, standard deviations, right, our posterior standard deviation, which literally is the standard deviation of our posterior sample, is larger than our standard error from our least squares estimates. Anybody want to take a guess as to why? I think I've said this before, but let's just refresh the memory. So least squares estimates can be our minimum variance, yes. But I would actually go a step further. It has something to do with how we handle our standard deviation, our residual variance. In least squares, we seek to minimize the amount of variance we have, right? It's the minimum of the squared difference between predicted value and observed value, right? We minimize that across the entire sample. So in theory, that minimum then starts to form, that value starts to form the basis for what we call residual standard error or residual variance, right? It's not exactly that, but it's close. That is really the issue, because in the Bayesian context, this is now a parameter to be estimated. And a parameter to be estimated means that there's estimation or posterior uncertainty with it as well. So let's take a look at that parameter for a second. Our least squares residual standard deviation was 7.949437. In Bayes, here's sigma. This is the posterior chain plot. You see my mouse moving over here. The posterior mean was 8.39. The posterior median was 8.23. So remember, this is somewhat of a skewed distribution, right? And we would expect that for a variance parameter with a sample size of 30 in a regression that has, or a linear model that has 6 fixed effects or beta coefficients. Yeah, we would expect our posterior distribution of the standard error to be non-symmetric, mainly because if you think back to, well, I don't know if you've actually learned this, but sampling distribution of variance is a scaled chi-square, effectively. There's more complicated versions to it, but think of it that way. And so that value, that distribution, when you have a small number of people, tends to be skewed positively. So the mean is pulled more than the median. So they don't look the same, right? And here is that distribution itself. Well, it turns out we could also look at, the question I have is this: is it all that different? Is it because it varies? Or is it because of our posterior summary, right? So remember, what we're looking at here is the mean, which is, right about here, or the median, which is the 50th percentile. But if we really want to look like what we would get in a maximum likelihood algorithm, where we could actually estimate this as a parameter, we'd have to take what's called the posterior mode. Now here the posterior mode happens to be 8.02. This is an MLV function for figuring out posterior modes. The mode of a density, by the way, is the peak, is the value where the peak of the density is. And the mode in a discrete distribution is fairly easy to calculate. It's the category that has the highest number. In a continuous distribution, you have to sort of approximate what that highest number happens to be. So a mode estimate isn't used very often in Bayesian because it's sort of a fuzzy point estimate of where that happens to be, whereas a mean is much more accurate. But here, 8.02 is getting closer to our point estimate from the least squares itself. So the answer, or the conjecture, the part I'm telling you here is why the standard error is bigger. Because turns out the formula for standard error involves the residual standard deviation, residual variance, which actually is sigma squared times x transpose x inverse. Right? There's some stat trivia for you. So think of it this way. If your standard error, if you have 1 sigma squared, you use that and you calculate your standard error. But in our case, we have a posterior distributions of sigma. Look how long the range is, right? So because we're using that affects the posterior distributions of the other parameters as well. And that's why our posterior distributions are actually quite wide here. So if you want to see this in case in point, what I'm going to do is run the same model, but instead of estimate sigma, I'm going to fix it to a constant, which is the value that we have right here in the data. Let's see what happens. of course, we have to wait for it to compile. Bayesian will teach you patience. I'm working on it with my 9-year-old. He needs to learn some more patience. Not quite going too well, but we just ran it. Let's take a look at the summary. Now it's taking a while. There it goes. Things have converged. Our maximum R hat. I'm not going to run each of these lines of code, but I'm going to compare the results now. Now, maybe. So what's taking so long is when you summarize, when you use the summary function, it's literally calculating mean, standard deviations, credible intervals, all on for every parameter in your analysis with this big Markov chain. So it takes a while to do the calculations. Here are the results. Now, do you see? These are much more consistent, right? So what I'm telling you here is several things. In Bayesian, when we define a Bayesian parameter, first of all, we are saying we don't know what the value of it happens to be. And the process of Bayesian is not trying to find its optimal value, meaning what's the minimum, right? Like the least squared version, but more so trying to build a shape of a posterior distribution itself. So that causes a few differences in estimation as we go. Standard errors are bigger, right? What can you think of? What does that mean ramification-wise for your data? What do you think? If standard errors are bigger in general in Bayes, just because of the estimation method, what does that mean? Less power. I'll go it that way. Although we don't really talk about power in a Bayesian sense because Bayesian hypothesis testing is a little bit abstract, right? It just means that you'll have more error in your results. Sometimes you don't want that, especially if you're in a field where P has to be less than 0.05 for you to get published. However, that is bad practice in science. I would say that Bayesian estimates can be more conservative if you think of them on their surface here. But I haven't gotten into priors and I haven't gotten into other information as well too. What do you think of this result? Is it interesting to you? Confusing? Different? Yeah. Think what you will. I'm going to keep moving. Yes, Vladimir, question. Yes, that's correct. That is correct. And actually, we're about to do that. Our next step will be investigating what we do with our prior distributions. Right now, I have not specified prior distributions. That means everything is uniform, which is the least informative that you would end up having. But yeah, that's right. If we put prior distributions on our parameters, that will also change things. This was sort of a start to sort of compare it to what you might already know with least squares and to get you thinking that the process of estimation adds uncertainty because all the parameters are trying to find a joint path to convergence. But yes, you're right. Now that we've established that the estimation process is different, we'll just accept that it's different and now add influence of priors as well too. Okay? Is that what you were looking for, Vladimir? Other questions? Thank you for your question, Vladimir. All right. No questions. Let's start with prior distributions. When you're new to Bayesian, if you're like me, you're like, gosh, what do I use for a prior? How do I build a prior distribution? Turns out, the first step in a prior distribution is to sort of match the parameter, the sample space of the parameter, onto a distribution to use it for. So let's break down what I mean. Let's start with sigma. Sigma is a standard deviation. Standard deviations we know have to be positive, right? So now, automatically, we know that we need a distribution that's positive. Right? So if I were to tell you, let's put a normal distribution on sigma, you might say, wait a minute, normals can be negative. That's not allowed. Correct. And stan, if you specify it as normal, it will actually truncate the normal at 0 and basically raise the mass of the normal distribution on the other side. But there are a whole bunch of other positive-only distributions. In fact, if we wanted to go, if you remember the stan website, MC stan, if you go to documentation and we go to stan functions reference, we can tell under continuous distributions, it starts with unbounded continuous distributions. That's not ours. We need a lower bound to it. But then there's positive continuous distributions. So now we can take a look. Any one of these positive continuous distributions, in theory, could be used to model variance. In practice, we don't often see that. And in fact, I remember when I was just getting started in Bayes in the early 2000s, there were a whole lot of people coming out trying to argue about which distribution will be right for a variance, and there's certain limit cases when variances head to 0 where things get fuzzy. But these distributions right here, in theory, could all be used. And one of the distributions I was going to start with, though, was an exponential distribution. So when you're wondering about distributions, first of all, think of the bounds of your parameter. We have a positive continuous distribution. All right, these are the options. I picked exponential. Let's go and investigate what exponential looks like. So why are we going through this process? What we're looking for, remember the idea of the probability density function. This tells us how relatively likely any value of this from this distribution is to occur. So an exponential distribution looks like this, right? It's positive. It potentially puts more mass towards 0, right? But if you look at, there's a single parameter in the exponential distribution. And as that parameter gets smaller and smaller and smaller, take a look at the height of the distribution, right? It gets lower and lower and lower. Of these three distributions, I'm going to ask you a question. Which one do you believe is least informative, is the most uninformative distribution if we were to pick it for a prior? Sergio puts down 0.5. You're right. It's 0.5. The reason for that is, at its peak of mass, it has a lower value of the y-axis than the other two. And you remember in Bayes' theorem, the part of the distribution that informs the result is how high the y-axis happens to be, right? We plug in a value of a parameter and we calculate its height on the y-axis. So you can imagine this exponential distribution could be fairly uninformative if our parameter for it keeps getting closer and closer to 0, such that it may start to look really, really flat. Right? So exponential is one distribution we could try. Any questions about that? All right, we're going to try exponential. Turns out here's the REXP. We can actually plot it ourselves. And I made a plot for you. This are exponential distributions right here. Right there. These are a plot. You can tell how informative or uninformative they happen to be. I did not put a legend. Oh, here's a legend. Where's my legend? Why did it not show? Y is 5, X is 50. That's why. Let's do X of 3. There we go. So you can see this is an exponential distribution. The parameter values range from 10, which is super informative, close to 0, to 0.1, which is fairly flat across the range. Okay? Questions? Now, let me start by saying this is an example. And in practice, I tend to not use exponential distributions on variance parameters, mainly because I want a little bit more than just one parameter to govern its shape. Sometimes I want to be able to move a location further. And the exponential distribution, this is why I love Wikipedia, its mean is 1 over its lambda, and its variance is 1 over lambda squared. So that parameter lambda informs the mean and the variance. So you can't separate the two of them very well in an exponential. But that being said, let's just give it a try. To put a parameter distribution in, like a prior distribution, under the model section, you take the name of the parameter, and you put this little tilde, and you tell it the name for the distribution that comes from the Stan user guide. So here under exponential, we can say y tilde exponential. And you'll note what Stan calls the name of the parameter may not match what the name of the parameter is in R or in Wikipedia, wherever you're looking to find this. So you may have to do a little bit more research to understand what the function happens to look like. In R, we have, you see, this parameter times e to the negative parameter times x. And in Stan, it's the parameter times e to the negative parameter times y. Well, y and x are the same here. This is basically the same shape, so the parameter function's the same. Why this is important is, again, some distributions in Stan may use a different parameterization than you're used to or that you learned the parameter for. So it's really important to check the parameter distribution in the Stan manual, even if you've used Stan for years like myself. Okay? So here, we're going to start with a 10 for the value of the parameter. That 10, as you saw with my plot, is highly informative, which means we would expect this well, no, we'll just say it. That exponential with the mass being right here towards 0 should take our sigma estimate and push it towards 0. That's what we would expect. So what we would expect right now from running this analysis is the point estimate, or the posterior mean, the posterior median, the posterior mode should all be smaller from this analysis than we did before. Should we try it? All right. I'm not going to talk too much here. We'll just let Stan do the talking. When was the last time you heard that promise from me? It's an empty promise when I say it. I always talk too much. You see that Stan actually ran faster there? Anybody want to take a guess as to why? Turns out Stan's process of sampling involves this Hamiltonian dynamics, which relies upon the shape of the posterior. Well, if the shape of the posterior is much more peaked, it's easier for it to go and figure out where that posterior is, which makes the process of sampling go faster. So it goes faster in this case. Kind of cool. Actually, no. The other reason is because I did not run it long enough. There we go. It still ran slightly faster. Not a whole lot. Come on, Templin. Pay attention. Yeah, that would explain it. I did it a tenth of the number. Yeah, it went as tenth as fast because it was like, sorry. You should expect better. All right, here's our results. Let's take a look. Did it converge? Yes, it did. Our R hat actually got better. That's what you're going to find. If you put more informative priors on your Bayesian models, it tends to have better convergence. But that's, remember, not because of anything about the data. It's because of your prior. Turns out, you can take a model that would never converge with uniform priors, an unidentified model, and make it converge in Bayes just with prior distributions. So that's dangerous, just mind you. This is part of why I like uniform priors. All right, let's take a look at our time series plots. Let's see if there's anything obvious that we can tell differently here. Probably not. Looks well behaved. Posterior histograms. I can't tell a very obvious difference here. But let's take a look at our summary and compare that to our previous model. So now these are all of our parameters. The last parameter here is the posterior, the residual standard deviation. So you can tell for many of our parameters, the posterior means are largely the same. Right? This is the first three columns here are the previous analysis, the one from the very first model where we estimated sigma. The last three columns are from the one where we have an informative prior on sigma. You can see that we've not completely changed our parameter estimates. They're largely the same for mean and median. However, their standard deviations Posterior standard deviations are much smaller. Right? So think about what we just did. We put a prior distribution only on the residual variance. Only on the residual variance, or standard deviation. And it changed and shrunk the posterior standard deviations for their coefficients. What does that tell you? Well, it tells us, again, our model parameters are tied together, right? And in linear models, this is, if you understand the linear model result that for what the asymptotic standard errors should be, they involve that residual variance or residual standard deviation. But now let's take a look at that parameter itself. Before, with an uninformative prior, we had a posterior mean of 8.39. Now with an informative prior, we have a posterior mean of 4.69. Much better. Oh my goodness. What do you think? Very different, right? Why do you think it's different? Well, let me just say why it's different. I'm short on time, so we're gonna keep going. It's different because two things. Number one, we did put a very informative prior on it. But number two, we only have a sample size of 30. If our sample size was 300, this prior would not impact this much. If our sample size was 3,000 or 3 million, it may not have an impact at all, right? Remember, in the Bayesian likelihood, the likelihood function largely is the data and then has the prior multiplying it. There's one bit prior and a bunch of data. So the more data we have, what we say is it overwhelms the prior. The prior becomes less important as we have more and more data. This is also a nice thing. All right, now if we compare that with our least squares estimates, you can see that now our posterior standard deviations are smaller than our standard errors, all through but just putting a prior distribution on. Pretty crazy, right? Oh, would you like to put a prior distribution on the coefficients too? I don't care. I'm still going to do it. You may not want to try it, but I'm going to. Now, our prior distribution for our coefficients. Let's think about building a prior for it. These coefficients, they can be any real number, right? So a nice choice of prior for any real number, I got to tell you, it's very common, but it is to put a normal distribution on as a prior. But let's think a little bit about what that might do. All right? If we say here, like in this example, I've basically just put a standard normal distribution on for each parameter, where the mean is 0 and the variance is 1. The standard deviation is 1. Do you think that's a good idea? I see heads shaking. Nah. Is that because you look at this point estimate right here of each of my parameters, and each one seems to have a very widely different value? Right? Think of it. Each one of these we are going to be forcing towards 0 with this type of prior distribution. Right? So let's think from a statistical point of view, if you're trying to not commit what we would call in the frequentist world a type 1 error, right? We would want them to be closer to 0, because the closer they go to 0, the more conservative our analysis happens to be, right? So that's fine. But this gets you thinking about what the parameters can be. Turns out each of these parameters has a different, not only mean, but look how widely different the standard error happens to be for each of these, right? Right? And that's because in the linear model, the scale of the parameter is in part due to the scale of the outcome, weight in pounds in this instance, but also in part due to the scale of the predictor, right? Because height in 60 inches has a much wider range, its standard error is 0.45. But factor diet group 2, that turns out to be a 0,1 variable, and it has a large standard error, right? So basically what I'm getting at is, in observed data world, you have to be very careful about picking a very default prior to put on everything, because you may end up having an impact. Let's see what happens. By the way, I'm also going to weaken the prior for sigma. So this 0.1 represents an exponential distribution with a plot that's even lower of a line, right? So it's a very uninformative prior on sigma, And I would actually say that a standard normal prior is a fairly informative prior for each of the betas. So let's see what happens with it. All right. And again, I ran it with the 1,000 chain. Let's see if it converged. It did. Let's take a look at our, there's our trace plots. How about some histograms? Oh, wait a minute. Things are very different here. As you might have guessed. Here's a comparison of effects. The posterior mean, this is, again, the very first analysis where everything had a uniform prior, versus this current analysis where we had an uninformative prior on sigma and a very informative prior on each of our values. I see some smiles on some of your faces. That's fun, right? What are you thinking? That's right. It's so, yeah, you've made this constraint. You basically forced each of the model parameters to be close to 0 because we don't have a lot of data. And because normal 0, 1 turns out to be a fairly informative prior, right? The mass of that distribution is between -3 and 3, 99% of the mass, right? So that means each of our parameters is going to be close to that on the coefficient side. Did you expect to see the variance explode? It did explode. Yeah, Sergio. Exactly. It is sort of like a centering issue, right? If each of these parameters go into what your predicted value is, and the residual standard deviation represents the standard deviation of what's left over, the farther off you are on your predicted value means the higher the residual standard error or standard deviation will go. So yeah, we've just exploded the variance. We've basically made a very bad model out of this, effectively. So yeah, the power of prior distributions can do this to you. And this is where Bayesian, the subjectivity, becomes a bit of a problem, right? So that's one of the issues. We're going to talk a little bit more about that as we go further in the class. I'm going to change things just slightly here and show you some stand-in syntax. You notice what I've ended up doing up to this point. By the way, if this bothers you, good. If these results bother you, make you worry about Bayes, absolutely. Very good. Be worried about it. Do not let it be. Let people know this. This is one of the pitfalls of Bayesian. However, we do have methods to check what seems to work better than others, right? We do have ways of looking at prior distributions that work with this, but it also tells you that if you were to report a result like this in a journal, and you said I used a Bayesian analysis, as a reviewer or as a reader of that journal with a critical mind, you would want to see the prior distribution specifications, correct? Right? So in a Bayesian analysis, because it's much more complex in terms of specification, you have to do a better job of describing not only what the priors happen to be, but why they're important. And then verify that the result seems to be relevant or meaningful. Because you can have an instance where prior distributions are completely off. Completely off. But actually, I think I'm going to stop here today. Let's think. I'm going to stop where we start to make stand syntax easier as a heads up for what we're going to do next time. What you've seen me do up to this point is whenever I wanted to add a prior or change a prior, I would change my stand syntax number 1, and then I'd recompile stand and rerun the model. What we're going to talk about on Thursday to begin with is how to not do that, how to build syntax that makes it easier so that the values of the prior distribution can actually be imported into stan as pieces of data. So then all you have to do is change your list of data, not recompile stan, and run the whole model as well too. So the process of building stan is somewhat like an art. As you're new to it, don't worry, be inefficient. Inefficient and inefficient's not bad if it's correct. Question in chat: Isn't a less informative prior had less effect? Why 0.1 prior had a bigger influence? So the question to answer that question here is yes, we had a uninformative prior on variance here. Yes, but we had a very informative prior on all of the means, all of the coefficients that go on the mean, and because these coefficients would likely, because they're so far, if we look at our first model estimates right here, this is what they'd be without a prior, effectively. That means that sort of tells me that in making predictions, like a predicted value from this result, our predicted values will be very far off from observed values. So that's why variance became very large. And actually, since I have a moment left, let me try this. If I go into this last model and I change our exponential to be a variance of 10, what do you think is going to happen? Are we going to have 147? Should we see? Probably not 147, but let's see what it ends up being. 41.4. And figure this, look at this actually here. Let's see if I can compare and contrast. Now each of these mean values aren't close to 0. They're a little bit higher up. So by putting an informative prior on the variance and an informative prior on the parameters, we ended up with a result that doesn't fit any of them very well. Not very good. Does that answer your question, Ryan? Hope so. Okay. Thank you. All right. Well, let's end today. Thank you for your time, your patience, your attention. Tomorrow, Thursday, we will start here and then go to lecture 3B, where we end on Thursday. I will create videos to be the end of lecture 3B and lectures 3C, and have a list for you when to watch those next week. I appreciate you being here. If you have any questions or anything to ask, I will have office hours tomorrow. I will not have them next week, but I'll have them tomorrow. And of course, Vladimir, our fearless and tireless teaching assistant, will have his office hours as well too. How's that for a plug, Vladimir? And I like each of you. You're all welcome to come. Okay? Even if you come and say, I don't understand, I will like to help you if you don't understand. All right. Have a great rest of your day and a great rest of your early part of the week. I'll see you Thursday. Thank you.